Hello, everyone. I am Jean-Michel Poggi, the president of ENBIS, the European Network for Business and Industrial Statistics. And I welcome you all to this webinar about statistical significance and p-values. ENBIS dedicates this webinar to the memory of Sir David Cox, who sadly passed away 2 weeks ago. Let us mention that he was active also in this controversial topic during the last year. The agenda of the webinar consists of a first hour with 3 short presentations given by Daniel Lakens, Bernard Frank, and Stefan Sen, followed by a 30-minute panel discussion chaired by Ron Kennett. This webinar, the aim is to provide an introduction and a review of a topic with very high current significant impact of the role of statistics in healthcare and beyond. Just for the organization, I would like to kindly ask you to mute your microphone during the presentation and during the discussion. If you have any question during the talks, please use the chat box to write your question, and Ron Kennett will organize the final discussion accordingly. The webinar will be recorded and it will be shared through different media channels. If you would like to access this webinar at another time, please note that it will be uploaded to our media center on the ENBIS website. For this, you need to be ENBIS members, so do not hesitate to join us for free. In this way, you will be informed of all the events organized by ENBIS. So welcome to our 4 speakers and thank you for being here. It's time now to start with the first talk given by Daniel Lakens, who is an experimental psychologist and is associate professor in the Human Technology Interaction Group at Eindhoven University of Technology. So Daniel, the floor is yours. You can share your screen to start the presentation.
Thanks, I will. All right, good. So thank you so much for the invitation. So I'll talk a little bit about the role of p-values in a Neyman-Pearson hypothesis testing framework. That's the plan for the next 15 to 20 minutes. And I just want to start by saying that it's important to always specify what kind of approach you're taking when you discuss a topic like this. Many discussions go on and on because people are not specific enough about what they mean and which kind of context they use, and especially which philosophy of statistics you use, which basically means that you have to ask yourself the question, what's the goal of statistical inferences? And I'll approach this from this Neyman-Pearson perspective and try to explain what the goal is and why it might be useful from this perspective. And my background is in psychology, so some of the reference you'll see is the discussion about this topic in my domain. So this is a pretty well-known paper in my field by Rosnow and Rosenthal, who criticize an approach to hypothesis testing. They say, well, it's not really about the logic itself that they're debating, nor will they discuss replacing alpha levels, which is a topic that comes up again and again and again. But they basically say we want to underscore that surely God loves the 0.6 nearly as much as the 0.05. Can there be any doubt that God views the strength of evidence for or against the null as a fairly continuous function of the magnitude of p? So this is, of course, one approach where people say, look, this kind of thing, we don't really want to have these dichotomous decisions. Now, this itself is something that Neyman and Pearson didn't agree with. This idea that what we are trying to do is quantify evidence or the truth or falsehood of a hypothesis. What they proposed in their original paper is, but we may look at the purpose of tests from another viewpoint. Without hoping to know whether each separate hypothesis is true or false, we may search for rules to govern our behavior with regard to them in the following, which we ensure that in the long run of experience, we shall not be too often wrong. So this is a different goal that they're trying to do. this goal of making these claims, these dichotomous claims without being wrong too often, has a specific background. And that is that in science, one of the things we're trying to do, or some people are trying to do, is to establish a corpus of findings, a set of findings which we all just say, look, this is sort of in the category of things that we now accept as a thing we can all build on and assume to be true until they're falsified in the future. Frick explains this. He says, in any case, scientists do not really seem to assign probabilities to claims. Instead, scientists act like the goal of science is to collect a corpus of claims that are considered to be established. So this procedure of making these dichotomous claims has the goal to establish a corpus of claims that we all build on. This process, in a Neyman Pearson perspective, does not depend on any individual's personal beliefs, which is attractive if in science we want to have a procedure that establishes claims that we all agree on are established, which is not the case if we let our individual beliefs determine whether something is made a claim or not. One of the best explanations of why we don't want this is from this paper from Taper and Lallet from 2011. They say, it is not that we believe that Bayes' rule or Bayesian mathematics is flawed, but that from the axiomatic foundational definition of probability, Bayesianism is doomed to answer questions irrelevant to science. Could hardly be more subtle, I say. We do not care what you believe. We barely care what we believe. What we are interested in is what you can show. So how would you do this? How would you show something? Well, in their view, they're likelihoodists. So they like what they call evidentialism, but they also acknowledge in the top here that a major rival for evidentialism as a philosophically sound, in our eyes, system for the advancement of science is the error statistical brand of Neyman Pearson analysis promoted by, for example, Deborah Mayo. And we see that it seems to be the case that researchers like to make claims. They do it in the titles of their papers. If you read them, those are often a claim, but definitely if you start to read the conclusions or the discussion section of their paper, they just make claims in these sections. So it's fine not to organize science in such a way. I'm fine with that, but it seems to be what some people are doing. So this is a way that we establish claims that either we think are established, but also sometimes we make a claim so that other people feel the need to challenge our claims. So there is a bit of a social role in this process where making claims also means that somebody will challenge this. And that's how we get, hopefully, some findings that withstand scrutiny. Now, of course, any claim that you make can be correct. It can be wrong, right? So how do we establish these claims? Well, we could use a coin flip. It wouldn't be very reliable. We would have a 50% accuracy rate if we just use a coin flip for every claim that we want to make. So what people have done, of course, is to increase the probability that we make correct claims. And this is where these hypothesis testing procedures come in. That's why they were developed, to make sure that we don't make a fool of ourselves in the long run all too often. This is also one of the approaches that David Cox in a 2020 paper says, yeah, this is one of those things which you would use p-values for, where they would be potentially useful. The first, he mentions a couple, the first corresponds closely to the considerations underlying the Neyman Pearson theory of testing hypotheses. So this is a case where these p-values seem to do something. Now, of course, people very often misinterpret what these outcomes mean. So they will say something like, okay, the p-value was significant, so now it is true, and all these kind of misconceptions. We know this, but formally, the idea behind using a p-value that is smaller than alpha to make a claim means that you would say something as the following. We claim there is an effect while acknowledging that if scientists make claims using this methodological procedure, which is what it is, they will be misled at most either alpha or beta % of the time. And we deem these error rates acceptable, which is something you have to justify for yourself, of course. And then you say something like, well, let's for the foreseeable future, until new data emerges that proves us wrong, assume that our claim is correct. It's a bit long for every test that you write down in your paper, but this is supposed to be the reasoning behind it. And again, when we make these kind of claims or decisions, sometimes people say, yeah, this decision-making stuff is nice if you work in a factory and you want to do quality control. But these decisions are slightly broader than this. And this is also from a paper by David Cox more than half a century ago. He writes, finally, it might be argued that in making an inference, we are deciding to make a statement of a certain type about the populations, and that therefore, provided that the word decision is not interpreted too narrowly, not only in the factory sense, the study of statistical decisions embraces that of inference. And indeed, this is also what Neyman here earlier sort of summarizes as his viewpoint of his procedure. He says here in the explanation of hypothesis testing, I hope to show that its constituent processes fall under three headings. First, we visualize several possible hypotheses. Okay, then we make some deductions from these set of hypotheses. And then the third step of the inferential process is an act of will or a decision to take a particular action. But this action doesn't have to be stop the factory. It can also be to assume a particular attitude towards these hypotheses. So when we accept or reject the hypothesis in this Neyman-Pearson approach to statistical inferences, we don't really communicate any belief about whether we actually think it's true or not, but we act in line with that it's true. Philosophically, the Neyman-Pearson approach is very strongly aligned to a Popperian approach, where Popper would say this is a basic statement. We make a basic statement about data we have observed in the world based on a pre-specified decision rule, the Neyman-Pearson procedure, for example, that the observed data reflect a certain state of the world. And this basic statement, of course, in Popper's approach would corroborate some sort of hypothesis or not. Building on this, you can call this methodological falsificationism. That's promoted by Popper, but much more developed later by Lakatos, for example. And in Lakatos's writing, we also see that Lakatos himself considered the Neyman-Pearson approach to rest completely on methodological falsificationism. So we have a statistical approach with a specific goal that is pretty well aligned in a philosophy of science that you can accept or reject, of course, but at least it's a coherent procedure. You don't have to do this. You can do something else. The alternative logically is either one of two options. So if you don't want to use an approach like the Neyman-Pearson procedure to make claims, then either you do not make any claims. It's possible. You write papers, but there are no claims in these papers. It's perfectly fine. You just describe something, but you don't make any claims. Or you make claims that have unknown error rates. That seems slightly unattractive. So if we don't use these p-values, which some people want to do for some reason, or these sort of claim-making procedures, then we also can't build a collectively agreed upon corpus of findings, or it will be very difficult to do, and I'm not completely sure how we would organize this. Or we make a corpus of findings that is wrong more often than we want. That doesn't sound particularly attractive to me. All right, thanks.
Thank you, Daniel, for this introduction. Very interesting. I don't see any question on the chat for this moment, so perhaps we could address a general question at the end during the final discussion. So, Ron, you want to say something?
Yeah, just to address the specific. So, Daniel, the point is that claims have some generalizability property, and that's considered in this Neyman-Pearson long-term approach, the generalizability of the claim.
No, that isn't part of it. And actually, this basic statement by Popper is really a statement that you could almost compare. If we wouldn't have probabilistic inferences, it is really the statement, I am now seeing a black swan. In our research, it's more often, these students perform better under this condition than under that condition. And that is the claim. It doesn't generalize to anything. You just say, this is now an observation I make. It goes into the pocket of established findings.
Thank you.
Thank you. Another quick question. No. So I propose to move on to the next talk. The second presentation will be given by Bernard Franck, who is a biostatistician in non-clinical and CMC statistics. He is a lead statistician with GSK Vaccines in Brussels. So, Bernard, if you want to start sharing your screen.
Thank you.
The floor is yours. Please.
Okay. I hope you can hear me very well.
Yes.
Okay, very good. So thank you. So this is the talk where we are going to discuss the p-value, of course, because that's the main topic of this webinar, but also the S-value, B-value, and D-value, which I think are not very well known. So just to introduce the topic, imagine you need a surgery. Which sentences of this one would you prefer your surgeon to tell you? And you see the first one here is very common. Usually we say, okay, the first treatment is significantly better than the other one with a p-value. But there are different ways to do this. And here in this talk, we will focus on the blue one here, which are very nice, I think. It's imagine you need a surgery and your friend as well, and you say, okay, if I go for the surgery A, my friend for the surgery B, will I recover quicker than my friend or not? And here, the last one here is to say, okay, but at the end, for myself, which treatment is the best for myself and not for my friend? And you see that this p-value debate is not new, actually. It started quite a long time ago. You see here a paper from the 60s, and it's quite controversial. You see here, no longer fruitful, defective, pointless, eliminated, attack, mystifying doctrine, desperation, impede the scientific progress. And the last years, we also had a lot of paper published here. You see the other statement is quite well known. And they mention here in this paper the prediction interval, but they don't explain the details. So that will be the goal here of the talk. And then you see here also the S-value published 3 years ago, which is nice. I like it. And the last one here, 2 years ago, actually, published by David Cox, which is also a very interesting paper. And you see about David Cox, actually, there is here a nice interview. You can read this interview. It's very interesting. And he was also involved, of course, in this topic about p-value and significance. And you can find on YouTube a talk that he gave 4 years ago. And you have also here a quote that I like about David Cox. So here, what do we bring here to this topic? Actually, we are going to compare the p-value, S-value, B-value, and D-value, but also to assess the uncertainty of these parameters. And we will show here that actually we can use also the tolerance interval. So tolerance interval, it is quite well known in non-clinical or industrial statistics, but it is rarely applied in clinical stat. This is the overview, so I'm going to spend some time on the one sample t-test because that's quite easy to explain. But then if I still have some time, I will explain the two arms, clinical trials and the crossover. And you see, actually, p-values and confidence interval is quite common. It is requested by most of top medical journals. And sometimes you can find stuff like this. You see researchers that are very proud to show tiny p-values. You see here, they even write it with all the decimal, all the digits. They even write, okay, 1 in 28 quadrillion. So they are very proud to show a tiny p-value. This is a nice paper also that I recommend to read about statistical test, p-value, confidence interval, and the power. And I like the 0.7, whether they say, okay, statistical significance indicates a scientifically important relation that has been detected. The answer is no. And you can even add, in medical research, the lower the p-value, the better is the treatment. This is something that some people think, but this is not true. So yeah, let's start with a toy example. So it's just a one sample t-test. You see here, we want to show that the systolic blood pressure is lower than 140. We have 100 patients. We have the mean, the standard deviation, and then we can calculate the confidence interval. So you see the confidence interval is here in red. And then we can say, okay, the confidence interval is lower than 140, so we reject the null. So it means that we can say, okay, the mean is significantly lower than 140. So you can, of course, calculate the p-value. So if you do it here, the p-value is 0.0098. It is significant because it's lower than 5. Then we can also calculate the S-value. I like it quite a lot, I must say, the S-value. In this case, it will be 6.7. And actually, the interpretation, yes, to say, okay, the p-value is equivalent of obtaining more than 6 heads in a row when tossing a fair coin. And you see here the S-value on the plot with the p-value on the X. It's just a line because I use here a log scale for the p-value. But I like the s-value when we have to interpret very small p-value. Now, okay, we can say, okay, what is the proportion of patients that have a systolic blood pressure higher than 140? And actually, we can calculate this with the normal distribution, and you see we have 41%. So you see the p-value was significant, but it does not mean that all the patients will have a systolic blood pressure lower than 140. And indeed, yeah, we have 41. So this is what we call the individual success probability. And now if I keep the same mean and the same standard deviation, but just changing the sample size here, you see I change only the sample size. You can see that the confidence interval, the p-value are changing. The confidence interval actually collapse to the point estimate. The p-value collapse quite a lot. The s-value will increase quite a lot, but the individual success probability remains constant. So that's very nice actually. Of course, then we can say, okay, but how to quantify the uncertainty about this individual success probability? So to explain this, let me come back to the concept of a confidence interval. So I think most of us here, we know this plot, and we have a mean here, for example, mu, and then the confidence interval at 95. It means that in 95% of cases, it will contain the true mean. And this is why people criticize this. And I think a lot of people, they prefer the Bayesian statistics with the credible interval, for example. But now if we go for the prediction interval, you see that's the same, more or less the same plot. Here, the prediction interval, the goal is to include one future observation. So the next one, and the next one here is in black. And you see that for an 85% prediction interval, in 5 cases here in red, indeed, they do not contain the next observation. And what I like here is that the next observation is random. So this is a common interpretation in frequentist in Bayesian. And now, yeah, the last point is the tolerance interval. So it's not very well known in clinical stat, but the goal is to cover at least 95% of the population. So you see the true interval is here. And the goal is to cover actually at least 95. And then we can add the confidence level, here's 90. And so indeed, we can see that in 10 cases, we have 10 intervals that fail. So the 10 intervals in red, they cover less than 95. So that's what you can see here on the graph here below. But otherwise, in 90% of cases, the tolerance interval will contain at least 95% of the population. So this interval is very well known in industry, in non-clinical, but rarely applied in clinical stat. And now what is nice with this interval, actually, you have here the formula for the basic one sample t-test. And if you make it equal to the hypothesized mean, so here it's 140, you can solve it for the coverage. So you see here it's in yellow. This is the non-central parameter of the t. And if you solve this equation, that's quite easy to do it. Then you can have the upper bound about the ISP. And you see in this case, the upper bound is 47. So it means that, okay, we estimate that 41% of the patient will have a systolic blood pressure higher than 140, and at most 47. So this is the 95% upper bound. You can do it also the other way. You can say that we have at least 53% of the patient that will be lower than 140. Of course, you can do it in Bayesian. So for the people here that prefer to do it in Bayesian, it's more or less the same because I use here a non-informative prior. So you see, I reached the same 47%. Now, if I come back to the table here, you see that by increasing the sample size, actually with the individual success probability, what is nice is that the estimate remains constant, but you see that we have a confidence interval that is added, and it will move closer to the point estimate. And then the interpretation is not confusing here. It's quite straightforward. If I take the one in green for 1,000 patients, we can say, okay, for at most 42.7% of the new patients will have a systolic blood pressure higher than 140. Something also nice here to see in red. In red, of course, I did it on purpose. You see that the test is borderline. Indeed, the classical confidence interval is 140, p-value is 5, and the confidence interval for the individual success probability is 50. So everything is borderline. And then now if we plot the p-value on the x-axis and the upper bound of the ISP on the y-axis, you see that we have a one-to-one function. And when it is borderline for the p-value, we are borderline with the ISP. But the advantage here is easy to interpret. We don't have tiny p-values. We don't need sophisticated rules to run the p-value. The interpretation is quite straightforward. And the cutoff value is always 50%, which is in a way intuitive because it's the middle of the scale for probability. Now, if we go for a 2 arms clinical trial, so it is here a basic 2 samples t-test. You see here I simulate 5 clinical trials by increasing the sample size from 50 to 5,000. But the means and the SD are identical. And so you see that the treatment, the difference between the two treatments are identical. So now if we calculate the p-value and the confidence interval for the mean difference, this is what we get. And we see one more time, if we take 5,000 patients, you see that the p-value is highly significant. So the p-value is tiny. The confidence interval for the difference of the two means you get here, so it does not include 0. But if you see this with a tiny p-value, then the researchers in medicine, they will be very happy. And it will be marked maybe as a 3 stars treatment in the medical journals. But now, okay, you can say, okay, if I undergo treatment A and my friend undergo the treatment B, what is the probability that I will recover faster? What is the probability that the success will be greater for me than my friend? And so this is what we call here the probability to get A higher than B. And this is what we call the B value in the literature. And we can also do it the other way. This is what we call the D value. And now here, if we do this, this is what we get. And you see that if I come back here to this example with 5,000 patients, the p-value was tiny. So it can give an impression that, that the treatment is incredible. But now if you look here to the individual success probability, we can see that at most 47% of the new patients are expected to get a better clinical outcome with treatment A than B. So still 47%. And now in blue, I like it. Of course, I did it on purpose. You see that in blue here, the test is borderline. With 500 patients, you see the p-value is borderline, it's exactly 5%. The confidence interval is exactly 0. And the ISP, the upper bound, is exactly 50%. Now, what about a crossover clinical trial? So here, let's say that we want to test if there is a difference between two treatments. And here, the difference is that we can still answer the same question. If I go for treatment A and my friend for treatment B, we can compare. But then we can also say, okay, if I undergo treatment A instead of treatment B for myself. And we can do it because in the crossover trials, we have the joint distribution. But you see that at the end, it's still a one-to-one function. So we have the p-value here on the x-axis, the ISP here on the y-axis. And then the difference here is that we can answer the two questions. So here in red, this is the individual success probability if I compare to my friend, which is independent of myself. And here in blue, this is if I compare to myself. So if I take the two treatments, which one will be the best for myself? And the reason why we have a difference here is just because if we do it in a crossover, we know that we have a correlation to take into account. So actually the distribution for the difference in the two treatments is much narrower. And so you get here an example. And so for here, in this example, if I compare to myself, I can say, okay, I have at most 44% probability to be better with treatment A instead of B. Now, a real example, just to finish, it's an orthopedic surgery study. It's also nice here just to show here this book, Information Quality by Ron, which is very nice. And then you see here the 4 different questions that we can answer. What is the goal of the study? Here with the real example here that we have, the goal is to study the accuracy of a surgical cut. What data will be analyzed, what kind of analysis will be conducted. And then we have also here different quality dimensions. And the one that I will focus here to finish the talk will be the communication point. So this real data, we have different variables, 2 surgical techniques, a freehand and a navigated one, 4 slices, because to remove the tumor, the surgeon needs to cut in 4 different directions. The surgeon, of course, it's a random effect. The primary outcome, it is what we call the location of the cut. It is in millimeters. The lower, the better. It's a log normal distribution. And the model here, it's a mixed model on the log scale. And now if we compare the two surgeries, so the freehand and the navigated, we can do it here for the 4 slices. And you can see here the individual success probability for each slice. Now you say, okay, if I undergo the freehand surgery in my friend the navigated one, what will happen? And you see that we have at most 20% probability to have a better surgery with the freehand. You see the point estimate is 12% and the upper bound here is 20%. I think here, this is my last slide before the conclusion. Here it is the summary of the statistical result. So you see we have the 4 slices, the confidence interval, and I didn't insist in my talk, but the confidence interval it is also quite controversial, especially here because we use a log normal distribution. So when we go back to the normal scale, actually here it is a ratio of geometric means. And you see here we have the confidence interval, the p-value. You see the p-value if you compare the 2 surgeries are tiny. It's very, very small. The S value, it's very big. And then we have the B value or the D value. And if we compare this, we believe that actually this one is better to interpret. As I explained during the talk, it's the same. P-value, S-value, or B-value, it is the same. And I prove it in a way in the talk by showing you the test when it is borderline. When it is borderline, all the tests are borderline. So actually it is exactly the same. But the B-value has more pragmatic interpretation. And you can see here, for example, with the freehand technology, we still have 20% probability to end up with a better surgery than the navigated one. To conclude, so maybe you can think this is not related, but let me ask you this question. When you bike, do you mainly use the front brake or the rear brake? So you can just think a few seconds about this. And actually, if you ask this question to yourself or to your friends, I think most of the people will tell you we use the rear brake. And why? This is because we learn it. But actually the truth is not. We have to use the front brake. And just to finish this analogy here, the rear brake, I think in my point of view, is like the p-value or the confidence interval for the means. There is nothing wrong about that. But we can do also much better. For example, the prediction of the tolerance interval that were mentioned in the ASA statement, but they didn't give so many details. So I hope this talk was very fruitful for this. We can use the individual success probability or even the Bayesian statistics. And just to finish here, confidence interval or p-value, they can be confusing or controversial. They can be confusing, especially for non-statisticians, which I think I don't blame them. It's true, it can be confusing. But the individual success probability here, we have a straightforward interpretation. Thank you.
Thank you, Bernard, for this very interesting talk. I have some time for a question, and perhaps Stefan, you can open your microphone and just ask directly or address your comment to Bernard.
Yeah, it was just that I think there's a danger, Bernard, that in your discussion of the systolic blood pressure example, that people will assume that you can classify patients in this way, but you had only measured the patients once. So you do not know with that example how much of the variation is variation within and between patients. And if I were to play devil's advocate, I could say maybe all the patients have exactly the same long-term average blood pressure. How do you know that's not true?
Yes, let me think a bit about this. We can complexify the example also. Here it was a toy example, because if I take it here, this one, when I simulate here, I use a within and a between variance.
Yeah, there you have a crossover trial, exactly. But the fact that the crossover trial would give you a different answer shows that you cannot trust the answer from the parallel group trial. It does not have that interpretation. Demi Denkov wrote this paper about the D-value in the American Statistician. I submitted a letter which was not published, pointing out his interpretation was wrong, but eventually a letter was published by Sander Greenland and others pointing out that exactly this false interpretation of the d-value is made. You cannot interpret it causally in this way.
Okay.
It's easy to see this because consider the following example. You draw a normal distribution. Then you move every point one standard deviation to the right. That means every single patient has increased by the same amount. The two distributions will overlap. The overlap does not tell you what proportion of patients respond. So I'm with you on the p-value, the s-value, and the b-value, but please put the d-value in the bin.
Okay.
Thank you, Stefan, for this question comment. I will share with you the question from Elena. Bernard, I am a social scientist who recently started working in healthcare research. I see studies based on convenient sampling, for example, online surveys or patient in treatment centers that were not selected at random, and they use significant testing, p-values, confidence interval, even regressions. Is it correct to use such statistics on non-probability samples?
I'm not sure to understand. What do you mean by no? You say non-probability sample.
I think it's not random, I imagine.
Hello, yes, not random. From what I know is that you can only use p-values if you're on populations on probability samples. So when you randomly select a sample from the population.
Okay, yes. Yes, I guess there is no issue with that. I'm not sure that I understand the question, actually.
So maybe I can explain what I think it means. Supposing you take a sample of voters to find out how they will vote in the next election, and you use a probability-based sample, either simple random sample or cluster sampling or whatever, then using the theory, you can calculate confidence intervals, p-values, and so forth. But supposing you just ask 1,000 people without selecting the sample in any particular way, this is a convenience sample, you just got 1,000. Can you then say anything? That's how I understand the question, but maybe I'm wrong.
Yes, thank you, indeed.
So you just select, 1,000, a sample of 1,000, that's what you say?
Yeah, so you do a poll on Twitter, right? And the people on Twitter reply, and you then say that shows that this is the way the country thinks. Well, obviously that's wrong.
Yeah, maybe to add, so it always depends. If the people on Twitter say what I also think is true, then it's a perfect outcome, of course. But the question is not so much about statistics, but about generalization. So the p-value is the p-value, but whether it actually generalizes to the whole population seems increasingly unlikely with a convenience sample.
Okay, thank you. So I propose to move to the last talk. The speaker is Stephensen, which is now a statistical consultant in Edinburgh, and has worked as a statistician and as an academic in various positions in Switzerland, Scotland, England, and Luxembourg. So Stefan will address now the significant issue. So Stefan, the floor is yours. I think that you are muted.
Okay, can you see my screen now?
Yeah, perfectly.
Okay, good.
But if you
yeah, put it on full screen. That's
okay,
right.
perfect. Thank you very much.
Okay, so I start with a couple of quotes from David Cox. The first one draws our attention to the fact that there is a different tradition for how hypothesis testing, significance testing works. The alternative hypothesis does not come first and tell us what the test statistic is, but in fact, we choose the test statistic first, and that then indicates what alternative hypotheses might be relevant. The second one is the one that we've already had ably demonstrated by Bernard, and that is that as the sample size increases for the same apparent effect, then the p-value just gets smaller and smaller. So this is what I'm going to talk about. I'll let you read that and I'll just carry on. So this is a phrase that you sometimes find. There was a trend towards significance. Funnily enough, you don't often see the phrase there was a trend towards non-significance, but maybe we should do. Maybe when people have p equals 0.04, they would say that the value has showing a trend towards non-significant. Or sometimes you find people say the result was not significant due to the trial being too small. Or they say things like, as more trials become available, the meta-analysis will be even more significant. Or maybe they say the trial was significant, so the next one should be also. These are all fallacies in my opinion, but the last one is actually responsible for misinterpretation of the so-called replication crisis. So first I want to deal with a red herring. The red herring is that there's some very fundamental difference between hypothesis testing, significance testing as proposed by Fisher or by Neyman. So Fisher stressed p-values, it said, you calculate tail area probabilities, you make inferences, not decisions, and he has no way of addressing the sensitivity experiments. On the other hand, Neyman Pearson were all about hypothesis testing. They use fixed type 1 error rates. They make decisions, not inferences, and they solve the problem of sensitivity by using alternative hypothesis, and in particular, the important concept of power. But the history is not like this. On the left-hand side, you have, in fact, tables of T introduced by Fisher. And the interesting thing is that you enter the tables by the fixed significance level. In other words, they're exactly the tables you need if you're going to reject or accept. If you want to interpolate the p-value, then they're not particularly useful. On the right-hand side, you have a quote from Lehman, often regarded as being the perfect disciple of Neyman. And he says, you should calculate p-values. This number gives an idea of how strongly the data contradict the hypothesis and enables others to reach a verdict based on the significance level of their choice. So here we have Lehman, apparently the perfect Neyman Pearson disciple, actually telling you to interpret p-values in a strength of evidence sense. Basically, I find no difference between the two approaches. You can say that you're going to be Neyman Pearson, you can say that you're going to be Fisher, but in the end, you end up using p-values the same way. The differences are really quite different. The issues that differentiate, in my opinion, are power versus likelihood, where the Neyman Pearson theory suggests that likelihood justifies power. That's the real reason you're interested in likelihood, is because it produces more powerful tests. In my opinion, this is exactly back to front. And Fisher was right in thinking likelihood as being fundamental and power as being either irrelevant or a sort of incidental bonus. The Neyman Pearson view is the alternative hypothesis dictates the choice of test statistic, but in actual fact, Fisher's point of view is this is ridiculous. You couldn't possibly know which alternative hypothesis would be true if the null hypothesis were false, unless you had had extensive experience that a particular test statistic was more sensitive than another one. Conditioning, Fisher regarded conditioning on relevant subsets as being crucial, and Neyman seemed to sometimes use the argument that overall randomizations, this is okay, we don't have to consider subsets. And the sensitivity of the experiment was power for a given alternative for Neyman, its precision for Fisher. However, I think it's useful to consider some properties of p-values, and one way is to have a look at the probability density function of the p-value. And what I've done here is I've plotted the p-value in terms of the power. The horizontal dashed line at the bottom at a height of 1 is under the null, and then these other curves are the probability density functions of the p-values for different degrees of power. And this is something I think that frequentists, and I count myself as being a frequentist, should maybe consider more often. And that is that if you have a look, for example, at the power of 99%, you will find that for a p-value of 0.05, it's actually less well supported under the alternative hypothesis than is the null hypothesis. And one way of seeing that is if you've got so much power, you should expect a really, really small p-value. If the alternative hypothesis is true, the fact that it's not really small maybe suggests you should consider the null hypothesis. So my view is the following: p-values are more useful than significance, even if you want significance. They provide a limited but useful function as one form of a surprise index, but I'm not suggesting you should use p-values all the time. And in particular, if you can do better, you should use other approaches. But whatever you do, a p-value is not a movement, it's a position. No p-values are trending. No p-values hold the promise that they will be repeated or that they will get smaller or whatever. And this is a fallacy, in my opinion, that some discussions of the replication crisis have fallen into. So here are 3 questions we might be interested in. What is the probability that in a future experiment, taking that experiment's results as on its own, the results would favor one rather than 2? Not conclusively favor one, just in the right direction. Question 2, what is the probability having conducted the experiment and pooled its results with the current one, the results would favor 1 rather than 2? And 3, what is the probability of having conducted a future experiment and then calculated a Bayesian posterior using an uninformative prior, and the results of this second experiment, the probability that 2 would be worse than 1 would be less than or equal to 0.05. In a sense, the last one is the replication probability. In the diagram on the right, just concentrate on this one, which is given by the blue curve. The x-axis is the ratio of the standard error to the first experiment to the second. And what you'll find is that as you move to the right, the second experiment gets bigger and bigger and bigger. If you stop at the point where the second experiment is exactly the same size as the first one, standard error ratio of 1, then in that case, as Goodman showed some years ago, you could plausibly argue that the probability of replication is 1/2. Half the time, the new p-value would be less than the previous one and half the time bigger. And some people would say, well, that's a disgrace. That's a problem with p-values, but is it? Because now consider another problem. You're going to do 2 similar experiments and you can choose any statistic you like, Bayes factors, whatever you like, whatever your favorite is. And you calculate the statistic for experiment 1, independently of experiment 2, and call it S1. And then you calculate the statistic for experiment 2, independently of experiment 1, and call it S1. And assume that nothing else is known. For example, you've not yet seen the results, and the following is true. The probability that S1 is greater than S2 is equal to the probability that S2 is greater than S1. And this applies for anything. So it's hardly surprising if your standard of success is to do exactly as well as you have done the first time round, that you're going to be disappointed half the time, the second time. I do stress that these are probabilities in advance of conducting the experiment. Once you've seen the experiment, you may have other information which can enable you to argue differently. So this property is shared by Bayesian statements. In fact, it follows from the martingale property of Bayesian forecasts. Hence, either the property is undesirable, and a criticism of Bayesian methods also, or it's desirable, and it must be a point in favor of frequentist methods. But my own view is it's much less important than many suppose. We're interested in the truth, and replication is only a means of getting there. A trial that is no more precise than the first one is only a very imperfect judge of the truth. The fault does not necessarily lie with the first one if the replication is not perfect. So now I'm going to consider the practical implication in drug development. This diagram is just supposed to show the 2 trials rule. The FDA likes you to have one result that's significant and then another one to show that it wasn't a fluke. And so this is the sample space that you would see. And here I'm going to generate some values. I'm going to assume that a strict point null is true with probability 0.5. And that the alternative hypothesis is true, but I'm not going to use a point alternative. I'm going to center it on a non-centrality value of 2.8, which approximately corresponds to 80% power, but I'm going to allow it to have a standard deviation on the true result by 1. And I'm then going to generate some results. And on the left-hand side, you see generation results that I got. Now, the ones that are red are under the alternative hypothesis, and the ones that are blue are under the null hypothesis, and those are my significance boundaries. This is it magnified, and the table gives you the replication successes. In fact, for example, it's quite clear that given those figures of 87 and 89 on the cross diagonal, that I'm not replicating perfectly. And I would say, so what? This is the same thing, by the way, if I use Bayes factors. So now I use a Bayes factor of 1/10. Here I also get a certain degree of replication failure. And again, I would say, so what? What exactly does this mean? It's the joint effect of taking these two trials together that matters. So let's have a look at this. Now I'm going to look at the two trial strategies, and I'm going to give myself the ability to know exactly what the truth is, if you like. But what I'm going to do is I'm going to run the second trial only if the first is successful. Actually, the number of false positives I will get, and here I require both trials to be significant in the right direction for me to claim a result, actually turns out to be 0 under the frequentist strategy. And this is probably a fluke, but under the Bayesian Bayes factor strategy, it turns out to be 1 out of 1,299. If I look at the number of false negatives, I get 68 for the frequentist approach and 68 false decisions. And for the Bayesian approach, I get 133 false negatives and 134 false decisions. But in actual fact, in the Bayesian approach, I less often proceed to the second stage. So it's a little bit unfair to compare them in this particular way. If I have a look at the trials per correct decision, then in that case, it's 1.47 for the frequentist and 1.5 for the Bayesian. Now I stress that different figures, different setups would give different results. But all I'm saying here is that anybody who talks about the replication crisis only in terms of false positives judged by what the second trial would show is looking at it in the wrong way, in my opinion. We also have to have false negatives in the situation, and we also have to think a little deeper. This is only my toy attempt to do so, but I'm just saying is be very, very careful about what you claim about decision-making procedures. So this does not show that significance is better than Bayes factors. Different parameters could show the opposite. It does show, however, that reproducibility is not necessarily the issue. The strategy with poor reproducibility is actually marginally better, but that doesn't have to be the case. But it shows it can be the case. It raises the issue of calibration, and it also raises the issue as to whether reproducibility is a useful goal in itself. And I should say, I mean, I don't want to offend Daniel here, but I'm not a psychologist. I was amazed at how well those psychological experiments stood up in the many labs work. If you'd asked me, I would have said most of this must be nonsense. I don't believe any of it. But in actual fact, the meta-analysis showed that an astonishingly high proportion of these so-called signal experiments stood up. I think it was only 2 or 3 out of something like 15 or 16 that were looked at that didn't. So the real problem is in the analysis. Standard errors reported as being smaller than they are. That's a very common problem. Holbert, in a nice paper from 1984, drew attention to pseudo-replication. For example, allocation of treatments to cages, but counting rats within cages as the N. Inappropriate experimental analog for observational studies, historical data treated as if they were concurrent. I think this is a fundamental problem for epidemiology. I think it's likely that in epidemiological studies, the standard errors that are calculated are quoted as being too small. What one might call block interaction problems, mistaking causal inference for predictive inference, causal, what happened to the patients in this trial, and then interaction does not contribute to the error. Fixed effect meta-analysis is an example. Predictive, what will happen to patients in future, and interaction should contribute to the error. And random effects meta-analysis is a sort of attempt to do this, not perfect, but a sort of attempt. So here's an example of pseudo-replication. I just happened to pick this because I'm rather nasty sometimes. I thought, well, I'll pick a Bayesian paper to show it happens as well. This is a Bayesian methods for the cross-design synthesis of epidemiological and toxicological evidence. But in fact, what they did was the data they took for the toxicological were experiments on pregnant rats in which the number of observations is the number of pups born to the mother, and you cannot treat these as being independent. In fact, the basic unit is not the pups, it's the mothers, it's the dams, and they did the analysis incorrectly simply because they treated this particular thing incorrectly, so they got an N that was too large. Other problems: publication bias, hacking, multiplicity in the sense of only concentrating on the good news. I don't actually think that carrying out multiple tests in itself is necessarily a crime, but it certainly is a crime if you just show the ones that you like. Surrogate endpoints are another problem, and naive expectations. Conclusions, I've nearly finished. P-values per se are not the problem, but there may be a harmful culture of significance, however this is defined. They have a limited use as rough and ready tools, but where you have more structure, you can do better, likelihood Bayes, etc. And I'm not anti-Bayes. I actually think that Bayesian analysis using carefully chosen prior distributions, but carefully is important, can be useful. We need to make sure that estimates are reported honestly and standard errors are calculated appropriately, and we should not confuse the evidence from a study with the conclusion that should be made. And finally, a quote from the Laws of Thought from George Boole: when the defective data is supplied by hypothesis, the solution will in general vary with the nature of the hypotheses assumed, which is to say that when you have to substitute a hypothesis for data, then in that case, there is a problem. But in worrying about the hypotheses, let's not overlook the effects of data. I'm finished.
Thank you, Stefan, for this very exciting and excellent talk. I will close this part of the of this webinar. Just technical information. Of course, we will try to collect, if the speakers are fine with this option, to collect the slide and put the slide with the presentation on the media center. So without any transition, I think it's now time to start the roundtable discussion chaired by Ron Kennett, who is the chairman of the KPA group in Israel and senior research fellow at the Samuel Neiman Institute at Technon in Israel. So Ron, the floor is yours.
Yeah, I'm still recovering from the from the talks. Stephen, your Q1 question, which is taking a directional perspective on the claim, on the result, is not how statistical analysis is set up to analyze data. It almost carries a verbal approach to present findings. You know, you're giving a sort of verbal representation of the claim. What is needed to address this type of approach?
I don't know. I don't know that that was essentially what I was trying to say. I wasn't really trying to suggest that question number 2 or 1 were important questions. I was just saying we had to maybe think about them and be quite clear as to what question 3 was. I think question 3 is somewhat interpreted. I mean, supposing I told you that I had a particular initial claim, but that actually, unfortunately, out of 20 further trials, only half of them actually verified the claim at the 5% level. So of those particular trials, half were non-significant and half were significant. Well, if you think about it, that's overwhelming evidence in favor of the original. Because the p-values should be distributed all over the range 0 to 1 uniformly if the original claim is not true, but actually half of them are less than 0.05. So that's overwhelming evidence for the first claim. So the question then is, if that's the case, why are people so upset when a single trial fails to replicate a result that was claimed previously? Obviously, it'd be nice if it did, but you know, that's...
Yeah. The quote on this, Gelman had this saying, people want certainty, but they cannot have it.
Yeah, I agree with that. Well, I often say a statistician is someone who prefers true doubts to false certainties.
Yes.
Maybe, is it okay to add something?
Yes, please. Yeah, of course.
Because if you have a procedure that's supposed to yield significant results, and in these replication efforts, they also try to get high power for whatever effect sizes sort of are supposed to be claimed in the original studies. And there's also some background information that we know very well that those original samples are, of course, not unbiased samples, but they have gone through a very severe selection process of publication bias, but also maybe of p-hacking and inflation. So you have to take those cases into account. There's a difference between making statements about what should be expected in a perfect world and in our messy world. Yes. That's I think where people were more upset than maybe a statistician thinking those people have been doing good inferences all along.
So this is what Yoav Binyamin is talking about, the selective bias, selective inference effect. But selective inference because of publication bias is difficult to assess. Selective inference in a publication which has 300 tables and only 5 of them are presented is easier to assess. Selective bias in the thinking process that precedes the research is impossible to assess. So it's a dead end. There's no way you can actually deal with this. There's always a limit. I have questions that were sent. Oh, okay. I can see some more on the chat. Oysten Evans, are you there? I think you are. Oysten had a question on the issue of practical significance. No. So I will.
Yeah. Am I with you now?
Yes, please.
Okay. I think that the author statement on p-values could have been conveyed more importance of a just a minute. Let me think. I think that the author statement on p-values could have conveyed the importance of recognizing the difference between practical significance and statistical significance to statistically uneducated readers more efficiently by using these terms explicitly than implicitly, the way this difference is accounted for in the document.
So I guess the question is what so we can have all the speakers deal with that. What is your understanding of the ASA? So we have the ASA official statement, and then we have the follow-up ASA American statistician issue. Maybe the bottom line is, did the ASA provide a service to statistics or a disservice to statistics?
I mean, the idea of the ASA statement on p-values is to learn statistically uneducated readers doing better work. And that could be improved with introducing explicitly the difference between practical statistic significance and statistical significance.
Yeah, I mean, maybe I can start replying. So I think this is a very important issue, and it is one to keep in mind when you discuss problems with p-values. For example, if Bernard presents that these p-values are getting smaller and smaller and smaller with sample sizes that become larger and larger and larger, but it doesn't necessarily mean that whatever you find is meaningful, then instead of looking at the p-values you compute, you could also say, well, what about the hypothesis I'm testing against? So maybe in those cases, I shouldn't have been performing a null hypothesis test, but I should have performed a minimal effect test. So I specify what actually matters, and then I try to reject or conclude that I can reject effects that matter or smaller, so that I conclude it matters, or the opposite, an equivalence test where you conclude, well, whatever is going on, it is too small to matter. And that would greatly improve things. And many of the misconceptions or the problems sort of identified with p-values as a thing become, well, they don't completely go away, but I mean, they're less severe if you would perform a test against meaningful effects. The problem is, of course, I think that the ASA has nothing to say about this, because those are content domain questions, and researchers should be motivated to have discussions within their field about what these smallest effects of interest actually are. And it's a super difficult question for many disciplines. Medicine, maybe a bit easier. My field, very difficult, but very important.
If I can say a few words, I agree, and I think it's quite common here in, for example, in pharma industry to use this. And for example, we can do a basic toast. But I think the most, so just a few remarks about this. If you increase the sample size, we still have a p-value that will collapse or reach 1. It depends of the margin, of course. But if you increase the sample size enough, the p-value for a toast will converge anyway to either 0 or to 1. That depends on the margin. I like it quite a lot. I think many people will like it, but I think the most difficult for this kind of test is the margin itself. Statisticians, we do not know if you tell me, okay, we want to compare 2 treatments for heart rate or whatever. I'm a statistician. I don't know very well which margin can I use. And if you ask the question to the scientist, actually, most of the times they do not know as well.
Stephen?
Hello?
Yeah. So, yeah, I mean,
I have another issue.
Yeah, hold on, Øystein. Let's have feedback from Stephen on this. Yeah.
Yeah, I mean, as Bernard showed very nicely in his talk, there is this this issue of the p-value seemingly just getting more and more interesting as the sample size increases, although the effect is not more interesting. Obviously, one way of dealing with that is not to rely on p-values alone. So point estimates and confidence intervals, but maybe also if you have a parametric setup, a likelihood plot, these sort of things I think are useful things to include. It is true that Bayes factors don't suffer from the same problem, but they do so at the expense of putting a lump of probability on a particular point of the distribution. And actually, in the field in which I work, drug development, it would be very dangerous to start using Bayes factors as a default. For example, if I'm comparing 2 particular beta agonists in asthma, then it would be ludicrous to assume that they could have exactly the same effect. That simply is not possible. If you were comparing a possible beta agonist to placebo, the effect might be 0 because the whole theory might be wrong and it might not work. But for them to have exactly the same effect would mean that you just happen to have found absolutely equipotent doses to compare to each other. And this is just simply impossible. So that's an example where you could easily get a very stupid answer if you started using Bayes factors automatically. And I suppose part of the lesson is you shouldn't use anything automatically. Or at least if you use something automatically, you shouldn't only use that automatically, you should use other things, because then in that case, they would give you the chance to see, well, okay, you know, the Bayes factor says one thing here, but the p-value says another. What's the origin of the difference between the two, and so forth.
So the automatically brings up, I was in a conference, mostly people from marketing, running, collecting million data points, running logistic regression with 25 covariates, and one after the other, this is the automatically, one after the other comes up in the talk with everything 3-star significant. At some point, it was funny. I was sitting there, it looked funny. at some point, someone will say, this is useless. Look, we're going through these motions that carry no value. You know, what's the information in this? There's no information. It's not informative. Randy Ellis had a comment that the paper, this is the Ron Wasserman paper, Moving Beyond the World with P less than 0 is not official, right? Oh, I cannot see it now. Is not an ASA official. So there was an official statement, and then there was the American statistician 43 papers, I think, collection, which came 2 years later. My take on this is that professional associations should open up a forum for discussion and not take sides, in a sense. Hi, Yoav. We talked about selective inference a few minutes ago. Do you want to say something about this? You are muted.
Yeah. If I may, first of all, as you say, even I was a member of the first ASA committee that tried to publish the first one, and it was not a consensus statement. That is, it wasn't agreed by all of us. And in fact, there are some 20 papers that disagree with the statement. The second one, the one that you mentioned with the 43 papers, it was not a statement by ASA. The invited people to the conference were opinionated in one direction. And even they, if you look at the summaries, agreed that the p-value is useful. There is a third statement that was convened of a committee that was convened by ASA in 2020. And we published our statement in 2021 in the Annals of Applied Statistics. This one was reached by a consensus. It reflects very much what Sam was saying, in the sense that the p-value is useful. And the p-value has problems, and significantness has problems exactly like other methods have. If you give a point estimate, a Bayesian point estimate, you have the same limitation if you use it by itself. If you give an estimate and you don't give the standard error, you have the same problem. You've used one of them. And the p-values is still the first line of defense against being fooled by randomness. And that's the important point to remember. Now, you mentioned selective inference. So that's a different issue. I was always talking about selective inference evident in the paper. Evident in the paper, you can see. We analyzed the 100 papers of the reproducibility study. There are 88 papers there that are p-value less than 0.05. And by attending to selection, 22 of the significant ones turned out not to be significant after attending to selective inference evident in the paper. And 21 of them were not replicated, and we lost only one replicable result by that. On another issue, which also was mentioned briefly on the issue of replicability, in animal behavior, we've been running a very large experiment in 3 laboratories, trying to replicate by using random effect and interaction of laboratories with the effect being tested. And by introducing that, we were able to reduce the replication rate from 60% to 12%. So the two issues, and I say that the two issues, the pillars of statistical replicability. One is selection. And many talk about selection that is not evident in the paper and try to emphasize selection that is evident in the paper. And the second one is hunting out the real uncertainty. This term, which was coined by Mosteller and Tukey. I mean, you should really try to reflect, and that was one of the questions there. What happens in the next time that blood pressure is measured? So that's the 2 points I wanted to make.
Thank you. There was a comment by Corley van Zyl on financial statistics. Is Corley available to make the point verbally?
Yes, I am available.
Okay, can you please share your experience, your feedback, your comment?
So what we often see in financial statistics or banking is where you've got a very large portfolio of clients, so 1 million or 10 billion, and I think the same thing happens in the telecommunication industry. Then the hypothesis tests always reject, because you always get the p-value beautifully close to 0. And that by no means imply that the result is actually significant. And that is quite a problem in the field, because the p-value is so well known. So whenever you try to use something else, it is not well received. But actually, there should at some point happen research into a measure, maybe the p-value in some other sense, or maybe another measure that gives better insight into what is practically significant.
Thank you.
Yeah. Maybe can I?
So yes, please.
Briefly add something. So I think if you take a look historically, the work by Neyman and Pearson was continued by somebody like Abraham Wald in the direction of decision theory, statistical decision theory. And you can take it a little bit further and then make it Bayesian statistical decision theory. And I think in a situation you describe, what you want to do is actually start to quantify costs and benefits. And then given some uncertainty, make some sort of decision based on data that you collect that will yield the greatest utility for whatever the goals of the company are in a given time span. And that might not be different enough, given that it's just a continuation of this thing we're already doing, that hopefully your colleagues will accept it.
So following up on this, so the p-value is people are used to it, they use it. Given what we know now, given the comments, the suggestions, the limitations that are being discussed, what would be the impact on statistics education? I mean, in other words, okay, so we want to do things differently. If so, what would be a different approach? So Daniel, what do you do in your class on statistics that is different?
I think to get away from the automaticity, you have to force people to be very specific about the question they ask. So I saw a comment that, yeah, some doctors might know what is important. In my experience, really many people you ask, so what do you care about? What do you actually want to find? They really don't know beyond somebody told me it has to be significant and that's it. But if you start to ask, so which effect sizes are interesting, they don't know. So very carefully thinking about the questions you ask. That's, I think, the one approach. And the other approach is to force people to justify all steps in the process. So if they set an alpha level somewhere, if they aim for a certain power, if they make assumptions about effect sizes that are meaningful, that they want to power for, all those choices should be justified. And that also goes against the automaticity. And then, yeah, sometimes the most beneficial outcome of that process is they decide they're not ready to test a hypothesis, which always makes me very happy that they realize that they're not ready to do this. And they first need to do some more descriptive research, for example. And that happens sometimes. So, yeah.
So, Stephen, do you have a comment on this? Educating people also in industry, in the pharma industry. I mean, like, or educating regulators. That is probably a bigger challenge.
Well, I feel a bit nervous because you never know if, some former students aren't listening in and they say, Sen can say what he likes, but he didn't teach us much. So I don't know. I mean, when I taught inference courses, I used to mix up the standard material with some nasty practical material. Students hated it, but I was to try and get them to think. So, a lot of it takes place in what I call simple random sampledom. So you assume that you have a simple random sample, you look at the properties of, how does the reliability of the median compare to the mean if you have a normal distribution, and what if it's Cauchy, and blah, 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 blah. And then I would throw in questions where in actual fact, if they read carefully, the data were not from a simple random sample. And then immediately they had to think, and none of this standard theory applied. And I think that's part of the problem, is that we stress the wrong things. A lot of more should go on design and really thinking carefully about data. And I always think there are two important questions that people should ask, in particular, for example, in regression modeling. They should ask themselves the following question: what am I trying to do? So is it an estimation problem, prediction problem, a classification problem? There are different things I might be wanting to do. First question. Second question, how did I get to see what I see? What has happened to the data if I didn't collect them before I got to see them? What other filtering processes are there in there? And I think a lot of these things are responsible for mistakes in interpretation. One thing that drives me crazy is the way that people calculate standard errors for the mean results in clinical trials, where, to revert to an earlier question, no random sampling takes place in clinical trials whatsoever. We never ever draw a random sample from any population. But on the other hand, if what you look at is you look at a comparison of groups, then we have methods to deal with that. That's a different issue. But nevertheless, New England Journal of Medicine, Lancet, British Medical Journal, all the time, standard error of the means, dynamite detonator plots, etc. Complete meaningless rubbish. So I don't know, somehow we have to get people to think about the things that matter.
So this was the question of Elena, the point of Elena on non-probability sampling. And
yeah, that's right. Yes.
Yeah.
Yeah.
There is a sort of conflicting view with algorithmic computer science groups which emphasize automation. They are looking for automatic solutions which are not requiring human intervention. So there are people who are for automation, and I think statisticians, at least it looks like statisticians here, are about combining automation with some specific thinking and considerations. This is, I think, against the current movement, where the solutions that are proposed are mostly automated. You are, and that's a big challenge, because the automated solutions are probably easier to sell and make, they have better PR than the statistical solution of, we need to ask questions, figure out, it's more difficult. There was a comment by Samira, which was referencing a book. Samira, can you tell us about this book?
Well, I've been looking at this initiative in Australia, which is choosing wise care, and there's been a lot. I think Australia has generally been ahead of the curve on evidence-based medicine, at least as it is being practiced now. And he goes through all these trials in orthopedics, and he's got two books. One about placebo, the uses of placebos in clinical trials, and the other one is a more general book, his latest, Hypocrisy, which is really covers that, it encourages patients to ask more precise questions than they do, and not just accept the statistics that are offered by the physicians themselves.
So patients have a role in their therapy, in their treatment. They are not passive, doing what.
Yeah, I think the issue is that there's been such a poor effort to educate the public. I mean, you've got Gigerenzer and a few others that try, but I don't think it's been very successful. And I would like to see more efforts by statisticians to address the public. But given that there's so many controversies, debates about p-values, it makes it extremely difficult. And I encourage my friends, and they do follow all of you, Ron, you and Stephen and Daniel and so forth. And we're dismayed actually that, there wasn't as much progress as there could have been. So that was what I meant.
Yeah, this obviously generalizes to engineering applications, drug development applications. You interact with domain experts, and they should contribute to the analysis. They are not just receivers. Here's the t-test. They should be able to participate actively. Whether statistics offers that or not is a question.
Yeah,
so
exactly.
That's why, Stephen, I think that presenting claims or hypotheses in a directional, almost verbose way would be a nice bridge to have this type of collaboration. Because they can respond to the claim. When this increases, this decreases. I think better than the coefficient of in this model is 1.625.
I think maybe to add, I think this is a really important point, and that as statisticians, maybe we like to just debate stuff among ourselves. And think about this ASA special issue. Like, there were how many papers? Like 43 different possible solutions of how to move beyond p smaller than. Well, I can't even keep 43 things in mind. So let alone that people who read these things know what we're going to do. So we could put in a little bit more effort to say, look, if you do this, you get this. We all agree. If you do this, you get this. If this is your question, you could do this or you could do this, right? It seems like there's a need. I think Samir is making a good point for the general public. Could be nice.
Yoav is burning in contributing something. So please.
I have compiled the table of the 43 papers with the rows, the papers, the columns, and in color, whether in favor or against. I have it in the Harvard Data Science Review paper, so you can enjoy it.
Oh, so yeah, send it to us. Send it to us.
So Jean-Michel, I think we are out of time. It's back to you. Yes. Samira, nice to meet you. We have so much correspondence.
I'm so glad to meet you too. I know Daniel and Stefan and Deborah, so it's a nice little group. My aunt was a mathematician and related to Frank Plumpton Ramsey, so that's how I became exposed to all of these statisticians from as a teenager. So it's still going on.
Nice.
Thank you all. I just read the conclusion from Andreas Georgiou. He wrote on the chat, thank you so much for splendid presentation and fruitful discussion. I have to leave. So I think it is a very nice conclusion for this. I would like to warmly thank you again, all the speakers in Ron, for chairing the discussion. Let me finally mention that the next webinar is scheduled for Wednesday, March the 9th at 12:30. And we will welcome Galit Shmueli, which is the editor-in-chief of the Informed Journal of Data Science. So thank you all and take care.
Thank you.
Bye.
Bye.
Thank you.